Hey friends, we are still in chapter 3, but we're coming to an end. We're here looking at linear functions and arithmetic sequences as linear functions. So let's start off with some vocabulary. We have a good number of terms here that we need to keep straight and make sure we have a pretty good understanding of. So we're going to take a look at the first term, which is a sequence. A sequence is a set of numbers in a specific order. A sequence of numbers that you guys are all familiar with are 1, 2, 3, 4, 5, so forth and so on. Another sequence of numbers that you might think of would be 1, 4, 9, 16. Can anybody guess what the next one is? 25. The next one, 36. These are perfect squares that I'm writing down. So a sequence is a set of numbers in a specific order. They can be negative, positive. They jump around. They move around according to a particular plan or rule. Terms of a sequence. Each number in a sequence refers to a term in a sequence. So if we look at the two sequences that we wrote up at the top, the first term of this first sequence is 1. The second term is 2. The third term is 3. Let's look at this other sequence. The first term is 1. The second term is 4. The third term is 9. So each number in a sequence is referred to as a term. So we've talked about sequence in terms. There's a specific type of sequence that we're going to talk about in this section, which is called an arithmetic sequence. It's a sequence that either increases or decreases at a constant rate. The first sequence that we have up here is an arithmetic sequence because it increases at a constant rate. The rate here being pretty obviously just 1. Another example of an arithmetic sequence will be for me to start at 4 and then add 5 to that and get 9. I can continue adding 5 and I'd get 14. Add another 5, I get 19. Add another 5, I get 24, and I can continue doing this forever and a day. That's an arithmetic sequence because it is increasing at a constant rate. This bad boy up here is not an arithmetic sequence. When I jump from 1 to 4, that's a jump of 3. Let's put that down there. When I jump from 4 to 9, that's a jump of 5. 9 to 16, that's a jump of 7, and you notice that there's nothing consistent here. So this is not an arithmetic sequence, all right? So now that we know what an arithmetic sequence is, we need to talk about something called the common difference. The common difference refers to the jumps that we make. So here in this first very original one, the jump was 1, or the common difference was 1. Here in this one, this sequence, the common difference is 5. The letter, by the way, usually referred to for the common difference is D. So D is the variable that we usually use to refer to the common difference. So D is the common difference. All right. So there's two ways of looking at formulas in general. A recursive formula is a formula that requires that you know the output before it in order to get the next output. So for instance, and this should be one word, my bad. For instance, let's say, look down here at this chart. Let's say we were going to look at this sequence in reference to the terms here. So here are the terms listed up at the top, term 1, 2, 3, 4, and 5. The first term is 3, the second term is -1, the next term is -5. Hopefully you guys can see that this is most likely an arithmetic sequence. We move from 3 to -1. That's a movement of -4. We're going down 4. We do that again. If we do it one more time, the fourth term in the sequence should be -9. What should the fifth term be? Notice every time we look to figure out the next term, we go to the previous output. That is looking at this particular problem in a recursive formula. So a recursive formula, a recursive formula requires that you look at the last thing to get to the next thing. So just to finish this off, the fifth term would have to be negative, what are we going down for? -13. Now the question that is answered by the explicit formula is, okay, so what's the value for the 1,000th term, right? An explicit formula will get you directly there because an explicit formula, sorry about my crazy line, An explicit formula is a formula that shows a relationship with each input to each output. So I can go to this 1000, I'm calling that an input, and I will get the output immediately. But notice if we look at this recursively, to get to the 1000th term, I'd have to keep subtracting 4, subtracting 4, subtracting 4, and I'd have to do that a whole lot of times. So the difference between recursive is that recursive and explicit is that you don't have to depend on the last term with an explicit, whereas with the recursive you do. And in the next section, we'll talk about how we would actually find the explicit formula. Okay, so the first thing we need to talk about is some notation. Oftentimes when we're referring to sequences, specifically arithmetic sequences, we usually use A with a little number below it to represent each term. So this is the first term, right? A sub 1 is the first term, the second term would be A sub 2, the third term A sub 3, and this fourth term A sub 4, blah, 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 and then all the way up to the nth term, which would be A sub n. So this is something that you will see definitely again, and we will talk about. And so we're going to use this to kind of think through the concept of recursive and explicit functions. Arithmetic sequences. Okay, so as we mentioned before, a recursive formula requires you to use the last number. So if I wanted to use the recursive formula to talk about this particular sequence, first thing, there's a couple things that I need to know. I need to know what the common difference is, right? Do you guys remember what the variable is that we used? Hopefully you remember it was D. So D is that number that I'm adding or subtracting, the common difference between each of the terms of my sequence. And so when I'm thinking about this recursively, if I'm looking for that A sub n term, I need to know the number that came before it. So if I'm looking at the nth term, I need to know the A sub n minus 1. That just refers to the term right before it. What would I do with that term? I'm going to add to it D. So this is considered a recursive formula. The formula is useful, but not super useful because I'm really required to know the number that happened right before it. So for instance, if I wanted to find out what the A sub 5 term is or the fifth term is, A sub n minus 1 will refer to the fourth term or the A sub 4 term plus D. So this isn't very explicit because I always need to know the one beforehand in order to get to the next one. So let's talk about the explicit one. There's a distinct formula that you need to know in order to get through or to keep in mind what's going on with the arithmetic sequence. So here it is. In order to find A sub n, you only need to know one thing, the beginning number. You don't need to know the number that comes directly before A sub n. And you also need to know the common difference. In order to calculate this, you take the first number, whatever the first number of the sequence is, you add to it 1 minus the n value, and then you'll multiply that by D. What is n? It is the value of, it's the whatever number term we're talking about. So let's look at this example. I have a box around the fifth term, which is 10 in this little pretty easy arithmetic sequence. And we're going to use this, we're going to pretend that we're looking for this fifth term, and we'll see how this explicit formula works. So to find the fifth term, the A sub 5 term, we need to take A sub 1, in this case 2. We're going to add to that n minus 1. Well, what's n? N is 5. So 5 minus 1 is 4 times D. What is the common difference? The common difference is the value that we see here as we move up. We're moving up by a common difference of 2. So if you notice, A sub 5 is going to be equal to 2 plus 4 times 2, which is 8, which gives me 10. If you play around with this, it will make a lot of sense. So don't just go, this makes no sense. Give it a try. Take a look at it. Look at the video a couple times if you need to. It will make sense. I promise. I know we spent a lot of time with that, but I think it was important. Now let's do some easy examples. Here's the first example. Determine whether each sequence is an arithmetic sequence and explain. So if we look at this first one, how do we determine if we have an arithmetic sequence? We are simply looking to see if we have a common difference. So as we go from -4 to -2, I recognize that as a leap of 2 negative 2 to 0, that's a leap of 2. 0 to 2, that's a leap of 2. Yep, we have an arithmetic sequence here, and we can explain that because of the fact that we have a common difference. We're going to do the same thing here, but fractions, I don't know about you, but I feel really uncomfortable. I like comparing fractions, or it's easier for me to compare fractions if I have common denominators. So I'm going to just rewrite these numbers. I'm writing equivalent values, but I just want to write them so that I have a common denominator. 16 seems like the best bet. So instead of having 1/2, I have 8 over 16. Instead of having 5/8, I have 10 over 16. Instead of having 3/4, I'm going to have 12 over 16. And finally, my last value of 13 over 16 already has a denominator of 16. So check the move, right? I see we've got 2/16 or 1/8. I can reduce that 2/16. This is looking like a arithmetic. Oh, no, it's not. Womp, womp, womp. We do not have an arithmetic sequence because the sequence continues on without having a common difference. So we need to check all that we have in order to determine that. And this last one is pretty easy because I think I talked about it before. 1 to 4 is a jump of 3, 4 to 9 is a jump of 5, 9 to 16 a jump of 7, 16 to 25 a jump of 9. This is not an arithmetic sequence either. So the only one that was an arithmetic sequence was that first one. In example 2, you're going to find the next term. Here we've got 15, 9, 3, and negative 3. We're going to find the next 3 terms. So sometimes I like to just write that out like that. And what I need to do is first find the common difference. It looks like we're going down by 6. So my common difference is a negative 6, and that's consistent. So we're going to just continue that trend. Negative 3 plus a negative 6 is going to give me a negative 9. Negative 9 plus a negative 6 is going to give me a negative 15. And negative 15 plus a negative 6 will give me a negative 21. And so we did that perfectly fine. We did not need to use the explicit formula because it was really easy to do that recursively. In this example, we're going to see the power of the explicit formula that we talked about earlier. Write an equation for the nth term of the arithmetic sequence. First thing we need to do is let's bring back up that explicit formula. We figured out that we can calculate a sub n, or the nth term. How? We can do that by having the first term and then adding to that the difference between n minus 1 times d, and d is the common difference. I know it was a lot, but let's see if we can use this to our advantage. What is our common difference? As I look here, I go from negative 12 to negative 8, from negative 8 to negative 4, from negative 4 to 0. What's that common difference? Hope you guys realize that it's 4. So d is equal to 4. So now all we need to do in order to write this equation for the nth term is go about our business and saying, okay, well, a sub n is equal to, what's the first term? Negative 12. Plus, what's n minus 1? Well, it just is what it is. It's n minus 1. They didn't give us a value. Times d, which is 4. I'm going to simplify this just because it's going to look more linear-like if I do that. So I'm going to leave my negative 12 here. I'm going to distribute my 4, so I get a positive 4n minus 4, right? And then I'm going to join like terms together. So finally, lots of work. My final answer is a sub n is equal to 4n minus 16. So this is the explicit formula. Now, I can be walking down the street and somebody says, hey, Dion, what is the 29th term of that particular arithmetic sequence? And my fancy explicit formula will do that. So nobody's actually shouting, Dion, what's the 29th term? But somebody is, the text, is asking us what's the 9th term. So if I want to find out the 9th term, I'm looking for a sub 9. So that's going to be 4 times 9 minus 16. That's what I'm going to use to get my answer. 4 times 9 is 36. When I subtract 16, I get 20. And so the 9th term would be 20. So that's my answer to part B. It says graph the first 5 terms of this sequence. We are going to skip that one for now because I really want to get to this last one. Which term of the sequence is... Here's what we do. We replace that with 32, and then we're going to solve. So that means the 12th term will be 32.